Hello and welcome to Rates of Change. This is an extremely fun topic. However, you will need to know how to differentiate. Just basic differentiations is basically all you're going to need for it. But it is a lot of fun. So let's get into it. All right, so we're just going to go straight in. I've got 3 different questions. By the end of these 3 questions, you should be pretty much set up to get going on your own. So the first one, we've got a circle's radius is increasing at 1 centimeter per second. So there's a random circle here. That radius is actually going to be increasing 1 centimeter every second. Okay, so it's getting larger. At what rate is the circle's area increasing when the radius is 10 centimeters? So let's have a look at the circle. All right, so here's the circle here. And we know that its radius is increasing. It's getting, wait, let me see if I can get this to resize. There we go. No, don't move. Resize. Okay, so every centimeter is getting larger, 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 and larger. And obviously, as the radius continues to increase, so will the overall area. Now, at some point, the radius is going to get to the size of 10 centimeters. And we want to know at that point, how rapidly is that area increasing? What you'll probably just notice from a common sense perspective is when the circle's very small, as it's increasing here, you see the radius, the area is getting larger, but it's getting larger quite slowly. But as that radius continues to get larger, the rate at which the area changes, sorry, this is really asking for such, there we go. I have to get right in the center there. But as it gets larger, the area is increasing at a faster and faster rate, right? Just a small change in area here creates a massive change in the overall area overall. And a small change in the radius down here, well, it changes the area, but not a whole lot. All right, so how do we do these questions? Well, what do we know? The circle's radius is increasing at 1 centimeter per second. So the rate at which the radius is changing, so dr dt, the rate at which the radius is changing with respect to time is equal to, well, it's increasing at 1 centimeter per second. So it's positive 1. The rate at which the radius is changing is equal to a positive 1. At what rate is the circle's area increasing when the radius is 10? They're asking us to find the rate at which the area is increasing with respect to time. How fast is that area increasing? This is what we're trying to find. Well, what do we know about the area of a circle? Well, we know the area is pi r squared, right? And from using that, we can work out by differentiating this, we can work out what dA dr is, right? If we differentiate A with respect to R, power down the front, 1 away from the power, we can work out what dA dr is. Let me rewrite it up here with the rest of the things that we know. Okay, so we know what dr dt is, we know what dA dr is, we're trying to work out what dA dt is. Well, we use this really cool trick. They call it the chain rule. Ultimately, all we're doing is timesing by 1. Let me show you what I mean. We're trying to find what dA dt is, right? We know that dA dt is equal to dA dt, right? Well, what we do is technically, one way to think about this is we're going to multiply this by 1. What's cool about timesing something by 1 is it doesn't change anything. It ultimately comes for free. But we're going to make the 1 look a little bit interesting. We're going to write our 1 as dr over dr. Can we all agree that dr over dr is actually just the number 1? But by writing it like this, it allows us to break up our fractions and rewrite it. I'm going to put that dr down the bottom over on this side. And the reason I can do that is because dt times dr is exactly the same as dr times dt. See, all I've done is just swapped the order of those two denominator terms. And by doing that, it allows us to rewrite dA dt as dA dr times dr dt. And we can all see, not that we want to, those drs would cancel top and bottom, just leaving you with dA dt, right? So we haven't mathematically done anything wrong here. And by doing that, we can now actually solve our problem. dA dr is equal to 2 pi r. I got that from over here. And we're timesing it by dr dt, which we know is a positive 1. That means the rate at which the area is changing is just going to be equal to, simplifying this, 2 pi r. And now that we know that, we can find the rate at which our area is changing. All we need to do is just sub in the r, and in this case, it happens to be 10 centimeters. So our final answer for this, I should say, when r is equal to 10 centimeters, dA dt will be equal to 2 times pi times 10. In other words, 20 pi square centimeters per second, or approximately, it was about 63 square centimeters every second. So by the time that radius gets up to 10 centimeters, the circle's continuing to increase. And at that particular moment, once the radius hits 10 centimeters, the overall area is increasing at approximately, or 20 pi, or approximately 63 square centimeters every second. So it's actually getting quite large quite quickly by that point. And that's how you do these questions. So the idea is you'll be given a rate of some description. In this case, we were given what dr dt is, right? This was the rate at which the radius is changing with respect to time. And let me just stick this in charge because I'm about to go dead here. And you'll be given some sort of relationship, or in this case, we had to write it ourselves, some sort of connection between the variables, the radius and the area. And fortunately for us, we already know the area of a circle is pi r squared. So we're able to use that relationship to then find our second rate, dA dr, and then we were able to use this chain rule. Let's look at that chain rule just a little bit more closely. So in this particular case, we had this, right? And the reason they call it the chain rule is because it's like we've got this extra variable which we called r. And the way that we can incorporate it is to throw it into the bottom and then bring it back up over the top on the other side. And we put our dt on the bottom over here. It allows us to introduce a new extra term or variable into our derivative, which, as you can see, was crucial for us solving this question here. And just like any chain, it can actually have more than just one link. You know, you could theoretically even introduce more variables. Let's say some hypothetical scenario where r is somehow related to some other variable called h. You could then, like, you know, daisy link in an extra variable, right? This here, this expression I've just written here is still just dA dt. Do you see how the dRs would cancel top and bottom? The dHs cancel top and bottom, just leaving you with dA dt. But by doing it in this way, this is, what they call the chain rule. And we're actually going to need the chain rule for all of these rates of change questions. All right, let's have a look at our next example. Okay, so we've got a spherical balloon. It's losing air at a rate of 12 cubic centimeters per second. right? So you think, what is a cubic centimeter? There it is there. You're losing approximately, 12 lots of them in terms of air, the volume of air, every second. So this balloon is dropping rapidly in size. So what we've just been told there is, right? So the air, so this is the overall size of the balloon. So in other words, the rate at which the volume is changing is going to be equal to, in this case, it's going down by 12. So our rate is going to be a negative 12. That was cubic centimeters per second. So we know what dV/dt is. We're trying to find the rate at which the radius is decreasing. So we're being asked to find the rate at which the radius is changing. They're asking us to find dr/dt. Okay, so this is what we're trying to find. And the only other thing we need to do is we need to somehow link V and R. And fortunately, we know the volume of, because the balloon is spherical, right? In this case, we have, do you know what? Let's make this a better sphere. Right, so we've got some sort of sphere. It has a radius. Bang, there it is there. And in this particular case, let's see if I have success here. Okay, so the balloon was here, full of air. There it is. And we know that there's, whether it's popped or there's a hole in it or someone's untied it, whatever it happens to be, the air is dropping out at 12 cubic centimeters per second. So the overall volume is dropping 12 cubic centimeters per second. So it's getting smaller and smaller and smaller. So that's what's happening to this particular balloon. We're going to find the rate at which the balloon is decreasing, or the radius is decreasing at 20 centimeters and again at 10 centimeters. Well, how can we link V and R? The volume of a sphere is 4/3 pi r cubed, right? You would have learnt about that formula back in your junior years of high school. So this is how we're going to link it. All right, so we're trying to find dr/dt. And so we're going to use that chain rule. dr/dv times dv dt. This is our chain rule setup for this particular question. We already know what dv/dt is, right? dv/dt was equal to minus 12. That's how fast this balloon is losing its volume. And the way we're going to find dr/dv, well, we know v is equal to 4/3 pi r cubed. Differentiating will give us dv/dr is equal to power down the front. So that will end up cancelling with the 3 on the bottom to just leave us with a 4. And 1 away from the power. Now this is dv/dr, but you can see quite clearly over here we need dr/dv. So what do? Well, we just do the reciprocal. Flip both sides. dv/dr, flip this, it'll just be 1/4 pi r squared. So we have dv/dr, we have dv/dt, so now we can go ahead with our chain rule. Right, dv/dr is just going to be 1/4 pi r squared. dv/dt is equal to a negative 12. So you end up with the situation where you get a negative 3 over pi r squared. This will be the rate at which the radius is changing at any particular time. And so all you need to do is, for part 1, I believe we had to let r equal 20. So dr dt will just be -3 all over pi times 20 squared, right? I'm just subbing it into this. And that will tell you how rapidly that radius is dropping. And just do the exact same thing over here. Now it's just asking you to put in a different value. Instead of 20, we're now letting the radius equal 10. And plug it in, get your answers, and ask yourself this question. Is the balloon, is its radius dropping quicker at the start or towards the end, right? At what point does that balloon really start dropping its radius at a faster rate? And this will tell you here. And the question hasn't told us what to round to, so you can put it in and round to whatever it is you like. All right, on to our final rate of change question. Okay, so this one here I actually stole from the textbook. The first two I just made up. Very generic, stock standard type questions. This one here was a little bit interesting, and I thought one that people might struggle with a little bit. So I thought I'll do it, you know. All right, so in this particular case, we've got this square pyramid. And there was some information telling us, you know, the height of the square pyramid is double the length of its sides, right? So, you know, we've got a square that's S across and S along, obviously, because it's a square. The height is 2S. It was just, the height was double. All right, so there's a diagram showing the words that were given in the question. All right, part 1 says, show that the surface area, which we're going to call capital A, is given by that expression there. So the first question has absolutely nothing to do with rates of change, no calculus at all. It's just a good old-fashioned, let's find the surface area of a pyramid. So let's do that over here. We have ourselves square pyramid. There it is. All right, those sides are S. The overall height is 2S. All right, so if you want to find the surface area, well, firstly, we've got a square on the bottom, right? So the area of that is going to be S squared. All right, congratulations, we've got that square covered. Now onto these 4 triangles. All right, let's find the area of these triangles. So I'm looking at this one here. For some reason, my eyes are just gone towards it. They're all going to be the same, so we can just find the area of one of them, times it by 4, and we should be pretty good. The area of a triangle, as we know, is a half of the base times the height. We know what the base is. The height of this triangle is not 2S. That's the height of the pyramid, right? And if we were to really look at what's happening here, bang, the height of the triangle is this side I'm drawing right now. That's the height from the base of the triangle right up to the tip. And the way we're going to find that is by, obviously, our good old friend, seems to be in every single topic we've done. No one thought in year 8 it was this important, not even me. It's Pythagoras' theorem. The guy is the winner of everything. So our height of our triangle is technically that there. This is 2S, and this side here, from the center across, is technically S on 2. How do we find this height? Well, we're going to use Pythagoras' theorem. It'll be the square root of 2S squared, in other words 4S squared, plus, what is that? S on 2 squared. So that would become an S squared on 4. I'm just going to simplify this down a little bit. I should have given myself more room. There's a bit of simplifying to happen here. So combining these 2 fractions, smile and cross, you get 4 on the bottom. You end up with 16s squared plus 1s squared. In other words, 17s squared here. And chain it back up here. Square rooting this. You know, we can't square root the 17, but we can certainly square root the S. And we can certainly square root that 4. Okay, this here is the area of just one of those triangles. I'm getting rid of all this. So, I should say the height of these triangles. So the area of the triangle is a half times the base times the height, which is root 17s all over 2. And so you end up with, in this case, s squared on 4 root 17. I'm going to write it this way. All right, so this is the area of just one of our triangles. So this surface area, bringing it back up to our surface area of the whole shape, we've got the square on the bottom, which is s squared, plus 4 lots of this triangle, giving us with, let's take the s squared out the front, 1 plus root 17. Which, yeah, okay, all right, cool. So this is exactly what we had. They threw the s squared at the back, which we can do it just to mirror the question, although you would not need to. You do have the question answered right here. Okay, so part 1 is done. We've found the area, the surface area of this pyramid. All right, so that's covered. Now onto the second part. Hence, we want to find the rate at which A is decreasing. So this surface area, we're going to find how quickly this surface area is decreasing when the side length is at 4 centimeters, and if the side lengths are decreasing at 2 millimeters per second. So I'm not sure what the original length of the side length was, but it's continuing to decrease by 3 mil every second. So I guess it's quite a slow decrease. This whole shape is maintaining its shape, right? It's just getting smaller and smaller and smaller. As you can see, 3 millimeters per second is how much is the decrease that's happening. And eventually the side lengths will hit 4 centimeters. It'll drop down to 4 centimeters. At that point, we want to find how quickly is the surface area decreasing at that particular moment. So, what do we have? All right, the side length is decreasing at -3. What does this mean mathematically? ds dt, right? The rate at which the side lengths is changing is a -3. It's decreasing. Now, I'm noticing a difference in units here. This is millimeters per second, and the side length up here is 4 centimeters. I'm going to convert everything to mils because I'm avoiding decimals, and it's easier to change a length than, having a muck around of changing a rate. All right, so ds dt is -3. We're trying to find the rate at which A is decreasing. We're trying to find the rate at which A is decreasing. This is what we're trying to find. And, we know the relationship between A and S, right? That was part 1. All right, so let's go on and do our question. Oh, and of course, we're going to let S equal 40 mil. Okay, so let's go on. So we're trying to find dA dt. So we're going to set up our chain rule. dA ds is our variable, right? That's the third variable in this situation, times ds dt. So we've used our chain rule to set it all up, and we know what ds dt is. We know what that is. That was -3. We don't know what dA ds is yet, but we do know that A is 1 plus root 17 s squared. That's meant to be a 17 there. So that will allow us to find dA ds. Use some calculus, power down the front. 1 away from the power, we have dA ds covered. And so now dA dt is going to be dA ds, which is 1 plus root 17 s times ds dt, which is a -3. And so there you have it. -6, 1 plus root 17 S. This is going to be, this expression here will tell us the rate at which the surface area is changing at any particular point. And all we need to do for the question that we've been given is just let S equal 40 mil, sub it in, and get your answer. And again, we haven't been given any guidance about how to round it or whether to keep it in exact form, so that is totally up to you. This is rates of change. So look back through this if you want. Look at the textbook. There's some Education Perfect lessons that I'll be included with this. They may explain it a little bit different, maybe a little bit more clearer than what I've done here. Look through, make sure you're good, and make sure you can do those questions. Let me know if you need any help, and I'll see you next time. All right, best of luck.